Well, welcome back, everyone. I think it's start time enough for us to start. Before we get started today, were there any questions folks would like to go over? Okay, just a strange comment that sometimes the pattern of how people sit is interesting. Today's class, the center is void and everyone's filling out the perimeter, so that's kind of neat. But we're almost through midterms week for a more related comment. So congratulations, we're just about over the hump. Like I mentioned, I'm about to put in midterm grades, but it's really just going to be your course grade that you see on the top of your returned exam too. I'm going to convert that to a letter grade by the syllabus, and that's going to be your midterm. So for the moment, we're in section 3.11, and assignment 8 is just going to be these two sections here. Now, sometimes in the reading, there's some sections that we're definitely not going to cover, and that would be this section right here in 3.11. So it's still interesting reading if you're curious about the inverses of hyperbolic functions. But I think that's an esoteric comment or concept enough that if you did need that information, that'd be something that everyone looks up or talks about for the first time. So that's kind of a strange topic. We're going to be dealing with just the ordinary hyperbolic functions. Well, any questions, folks, before we jump in? Okay, so now in section 3.11, I should clear this out. Here's how hyperbolic functions are first defined. So my notes are kind of strange because this is a brand new topic. First, I want to scroll through here just to show you what we're getting into. First, we'll look at the definitions of hyperbolic functions. We'll look how to define all of them. There'll be 6 of them, just like the trigonometric ones. Here, we'll just look at how to practice working with those. We'll consider what their graphs look like. This is really more of a reference for us at this stage on this page. So it's not information you want to try to memorize verbatim, unless you have a really great working memory. But then right here, we'll look at some identities, just like trigonometric identities. And finally, we'll get into the derivatives. This is where we'll spend some time looking at how to calculate with these derivatives. And so that's kind of the organization of the notes. If you keep scrolling through, we'll have an application to look at. And this is the optional material right here. It's still on the notes because, well, for the sake of completeness is what I put. But all the hyperbolic functions can be inverted on the right domains. And if you ever needed their derivatives, they're defined down here. But because this is optional reading, I'm not going to ask you to calculate the derivative of an inverse hyperbolic function without actually assigning one of these problems, which I haven't, or actually putting the formula on the exam itself. So these would be just, again, kind of extraneous topics at this stage. The ones we should expect for derivatives would be these ones right here. So that's our new list. Well, that's the organization of the notes. They're a little bit strange today because we're doing a topic related to trigonometry, but from a different point of view. Trigonometry, well, these are the weird things, to be completely honest. For a trigonometric function, the way we define it, really the best way to define the trig function is we define a unit circle, x squared plus y squared equals 1. Then at this point right here, we'll have a value of t, and at that value of t, the area of the sector right here, or excuse me, twice the area of that sector right there would be the value of t. Reason to mention that is it works the same way for hyperbolic functions. Then after you have this coordinate here, we just say that the cosine value is the x coordinate, so that's cosine there, and the sine value is the y coordinate. But what we never said is, okay, but what's the definition of cosine? It's left completely onto this geometric structure right here. We never fully defined it as an actual function, f of x equals do this as an operation. Hyperbolic functions you can, and that's what's really kind of odd about this. For a hyperbolic function, let me skip to the definition. Sine hyperbolic would be written this way, and it does have a definition. You're really just doing this all together, either the x or the negative. Sorry, say again?
No.
Was there a question on Zoom? Might be
No.
Okay, gotcha. No worries. So we have actual definitions for both the sine and hyperbolic cosine. That's really kind of nice. If I give you a number, you can just plug it in and crank it out. If I give you a number for, say, cosine, Well, now you have to think of rotations, where the terminal part is and what the x coordinate is. That's a whole different kind of ballgame. So trig is weird. And the reason we cover trig is, well, it's the applications are immediate. There's loads and loads of applications. But now let's go to the hyperbolic functions. Oh, I didn't mean to click that away. I hate it when they update Zoom. It's a whole new muscle memory to come up with. I think maybe over here is better. So now here's what happens with the hyperbolic functions. We change the curve from x squared plus y squared equals 1 to x squared minus y squared equals 1. Once we find a point t right here, that value of t for cosh t and sinh t will be such that t is twice the area of that shaded region. Now, the difficult thing about the hyperbolic functions, another reason it's not covered in place of trigonometry, is it does take a lot of mathematics, a great deal, to show that this property, t is twice the area of that blue shade region, really does hold. We need to know about integration to get to these kinds of definitions, which is chapter 5. But we can still work with it and see how this all goes. So we have cosh t. We refer to this as hyperbolic cosine. Just like before, the value of the hyperbolic cosine is going to be something right here, just like in the trigonometric case. For sinh t, sometimes I'll say sinh or sine h or hyperbolic sine. The hyperbolic sine would be this value right here, whatever it happens to be. So that's the diagram that defines the functions. Then an awful lot of mathematics is taken to show that hyperbolic cosine, this cosh value here, is truly defined in this, oh, didn't mean to scroll, truly defined in this way. For hyperbolic cosh, you just take e to the x plus e to the power of negative x, divide by 2, and that's the whole definition. For hyperbolic sine, it's almost the same thing. There's just a sign change right here and here. So usually the strategy is memorize one or the other. If you've memorized hyperbolic sine, do your sign change right here, and you have hyperbolic cosine. And everything else is similar. For example, in trigonometry, tangent of theta is sine theta divided by cosine theta, exactly like what we have right here. Cotangent theta would be cosine theta divided by sine theta. So hyperbolic cotangent theta is cosh divided by sinh. What's kind of amazing about this, and almost miraculous in a way, is you could literally take your 2-credit trigonometry course, flip the sign to negative right here, and just do hyperbolics. The same course could be read with different applications. Really kind of strange. So in a trigonometry course, first thing you do is you define the unit circle, then you define the functions, then you just practice evaluating the functions. That's what we'll do right here. Any questions first before we just practice working with these things? Okay, for this, you need to show steps, give exact answers in simplified form. And this is the same instructions for right here on the Moodle website. Oh, I didn't mean to scroll. That resets the view for some reason. So I just want to post this on the document to say on the instructions for this assignment, right here, we're doing problems like exercise 1, 2, 3, 4 with those instructions right there. So here's how it goes. If we want to evaluate hyperbolic sine h at 3, we just plug 3 in for the position of the x's right up above here. So this will be e to the power 3 minus e to the power of negative 3 divide by 2. Then at that stage, well, that's the exact answer. It's pretty much in simplified form. You could do a little bit more to it if you're worried about the negative exponent, but we never were, so I'd say that's just fine to leave exactly like that. We did it, well, folks, that's our first value there. If you want to throw it to the calculator to approximate it, that's completely fine. But when it says show exact solutions, this just has to be somewhere on the page, the exact value. Any questions at all, folks, on that one there? Okay, so if you get something like a 3 as your input, Usually your answer looks like this. It's kind of gnarly. It's off the base E exponential function. But if it involves a natural log, that one does simplify quite a bit. Because you're putting a natural log up inside here, there'll be a cancellation. So let's do hyperbolic secant natural log 10. Well, if it's a secant, that's a 1 over cosine, whether it's hyperbolic or not. So I'm going to be using this formula to start. This turns into 1 divided by cosh of natural log 10. So all I've done is bring in this function, because that's where I am allowed to finally put in values for x's and then start simplifying and evaluating. So now this thing is going to become, well, if you divide by cosh like that, you're just taking the reciprocal of this. It'd be 2 divide by e to the x, but the x this time is natural log 10. Then it'll go plus in the middle, e to the power of negative natural log 10. In a strange way, this course has lots of logarithms, even if we're not in a section dedicated to dealing with logarithms like 3.6. They just come into play all the time, it feels like. Here, this one does simplify, unlike the one above. We can get a more exact numerical value. So what we can do here is that's our standard cancellation. The base E exponential is annihilated when it's composed with the natural log function. They're inverses to each other. But this is a really, really subtle point in algebra. I can't cancel right here. Anyone see what the problem is on this one? It's the negative sign. That negative sign means the function is not natural log, it's negative natural log. Negative natural log doesn't have E as its inverse. There's no cancellation right here. But we can still simplify. Here's what we've got to do. Let me include some extra space just in case. We can take that negative right here, use properties of logarithms, and make it be an exponent to the 10 in this position. So this is the property I'm about to use. P times the natural log of A for anything is the natural log of A to the power P. So this time I'm doing it in reverse. I'm taking the negative, making it an exponent of -1. This then turns into 2 divided by just 10 right here. Then it's going to be plus e to the power of the natural log of 10 power -1. So all I've done is taken this negative, made it an exponent right here. And now in this configuration, there's no trouble. That is an immediate cancellation right at that stage. Does that make sense to folks on the weird issue with cancellation here and here? Okay, if we're happy with this, now we have a numerical result. It's 2 divided by 10 plus 10 power -1. That would simplify. What we can do to simplify this thing is 10 power -1 is really a 1 over 10. You can eliminate that fraction by multiplying by 10 over 10. Parentheses here, since we'll have to distribute. In the numerator, we'll obtain a 20. In the denominator, multiply this by 10 to start. We'll get 100. Plus, then 10 times 10 inverse results in just a 1. So it'd be 101 down below. So hyperbolic secant of natural log 10 is 20 101ths. Weird fraction, but it's kind of nice we can get an exact answer in that way. That's analogous to doing, say, sine of pi over 6 and getting a 1/2 out versus trying to calculate sine at 2. You get weird things out, much like this one here. Well, other questions, folks, before we try one more? Okay, let's see how this next portion goes. We're doing a cotangent. Although the formulas are up above and we're here just so we can get some white space, you can still follow your nose with your training in ordinary trigonometry. In ordinary trigonometry, a cotangent is a cosine divided by sine. So hyperbolic cotangent, cot h of 2, is going to be hyperbolic cosine in the numerator, cosh of 2, with hyperbolic sine in the denominator. So sinh of 2. So those are our values. Now we have to actually input them. And again, this is always a really great strategy. If you've memorized one function or the other, you have both. I'll do sinh here. The way sinh goes is it's e to the x. Our x value is going to be a 2, so I'll plug it in there. This is the one thing that changes, that minus sign. I'll highlight it in yellow. And above here, that's going to be e to the power of -2. So that's the function numerator for hyperbolic sine. Whole thing is divide by 2, but we're going to see that that division by 2 could be neglected in this problem, since we have 2 divisions by 2 in numerator and denominator. So now let's do cosh for the numerator. This will go, let me insert a little bit of space, e to the power 2. There'll be plus in the middle right here. And then the power on this e is the same as hyperbolic sine. So e power -2. Whole thing is divide by 2. And so now, well, we don't have to deal with those divided by 2's. We can eliminate them by multiplying by 2/2 like this. So now it becomes e squared plus e power -2 divided by e squared minus e power -2. So that's our resulting function on this one. It's exact. We showed the steps and it's in a simplified form. But much like this one over here, I really can't do much with it except maybe rearrange, get rid of the negative exponents. So I would consider this just as simplified as this one is right here. If you want to go further, put it in a different format. I'm going to delete this in a moment, but just in case you wanted to, you could do this to it. Multiply by e squared over e squared, and you could eliminate that negative exponent. Only reason you would ever want to do that is maybe you're checking out the back of the book, trying to line up their simplified form with yours. Well, that's the portion of the notes where we're just practicing with our new definitions for these functions. Any questions at all, folks, in dealing with them? Okay, so after we've taken a look at the definitions of the hyperbolic functions, we need to be aware of what identities there are out there. Our course aren't going to use these a lot. Here's the graphs again. Let me just put this back on this page. Our course won't use these identities a whole lot, but it's still good to be aware of them. If you're dealing with any kind of trigonometry, whether it's ordinary or hyperbolic, it's good to have those kinds of things on the table. For example, in ordinary trigonometry, this is our superstar identity, that sine squared of x, or theta, let's go with x, I'll be just fine, plus cosine squared of x equals 1. We have a related identity, but it goes like this. Cosh squared x minus sinh squared x equals 1 in the land of hyperbolics. Where does all this stuff come from? It's the original definitions of these functions. This is based off a unit circle, x squared plus y squared equals 1. And this is based off a hyperbola, x squared minus y squared equals 1. That's the only reason these two identities exist. And there's a whole bunch of other ones. For example, this identity says sine h of x is an odd function. Odd function is a way to say it would be symmetric about the y-axis as a graph. It's symmetric about the origin as a graph. You can reflect it across y-axis and x-axis, and you're not changing the graph at all. Let's see if that really holds true. Hyperbolic sine is this one right here. It's this little S-bend curve, and the dashed lines are just types of asymptotes that it's going to approach in one end or the other. But yeah, if you reflect this line across the y-axis, it would go like this first, reflect the black line across the x-axis, and it overlaps like this. It's symmetric about the origin. And so that's all that identity is about there. Hyperbolic cosine, this one's symmetric about the y-axis. That means it's an even function. And algebraically, an even function does this. It wipes out the negative sign, gets you back to ordinary cosh. Let's try that out just to see how it goes. Any questions so far, folks, about any of the identities? Okay, so I won't ask folks to prove identities in this course for hyperbolics, but it's good practice just dealing with these things. Because the first thing you have to do to prove any identity is, well, you need to know what is cosh x. That's going to be the right-hand side. Cosh negative x. That's the left-hand side of this identity. If we can make these become equal, then our work is done. So to start out, this will be e to the x, e negative the x, division by 2. And the middle, anyone recall if it's plus or minus? It'd be a plus, absolutely. So plus for this one, minus for side h. So, well, we're done on that side. That's what cosh should look like. Now for cosh of negative x, we're just plugging negative x into those two positions. Will be e to the power of negative x plus e to the power of, here, let's be careful, negative of negative x, divide by 2. Upon simplifying, we now have e negative x plus e to the x over 2. But sure, it looks different, but it is the same exact thing. The numerator, you could switch the order of addition, and we could say that this is equal to cosh x. So that completes the verification. We have shown that cosh negative x is really cosh x. It'd be symmetric about the y-axis, so it's an even function. So there's lots of other interesting things here. This is a core identity. This one right here is a related one, much like how we have, say, tangent squared x plus 1 equals secant squared x. Here in the hyperbolic land, it's just a little bit different. 1 minus hyperbolic tangent squared is the secant squared on this one. And these would be addition formulas, just here for the sake of completeness. So those are the identities. And again, I wouldn't say this is the major thing to put on, say, your page of notes for exam 3. We're just trying to get used to these new classification of functions with examples 1 and 2. That's the major takeaway point. The things that we would put on our notes are this kind of things. Again, I would say this is a good table to have memorized. But if you didn't have this one memorized and you're relying on your notes, that isn't terrible either, since these functions are a little bit more esoteric. But just be aware that in calculus 2, calculus 3 differential equations, these do come up. So it's good to be aware of how these derivatives should go. So here's what the table looks like. For dealing with the ordinary trigonometric functions, we had some interesting patterns that we liked, that we knew that were kind of awesome. If you differentiate a cofunction, you always got a negative sign, for example. And there's other interesting patterns there to help us out too. In the land of hyperbolic functions, there has been a change. Let me highlight in this way. The one change on this diagram or on the table is going from here to here. The negative sign has moved over to this location. Kind of strange, but that's the result of the derivative right over here. We could show it must be that case by, let's say, we differentiate this one right here and show we really get a negative sign. Or we could do this one. This one's odd too. It says, if you differentiate hyperbolic cosine, you get hyperbolic sine. Differentiate hyperbolic sine, you get hyperbolic cosine, and this is just a loop. It doesn't loop the same over here. This one repeats after 4 derivatives happen, since you have to worry about getting to the cosine again to kill off the negative sign. So let's maybe try, I'll leave it up to the class. Should we try the one on the left or should we try the one on the right? Good call. I think this one is pretty bizarre looking. So if we differentiate hyperbolic cosine, here's how the work is going to look on this one. Derivative with respect to x of cosh x. I mean, we do have the answer right there. It's sine h, but really we're doing a derivation on this one. On the next problems, we'll work out these as really more typical homework problems. The way this will work is we're taking the derivative with respect to x of, we need to put in the actual function, hyperbolic cosine. This becomes e to the x plus, because it's a cosine hyperbolic, e to the power negative x, whole thing divided by 2. So that's the thing we're differentiating. You know, honestly, this looks like a nasty derivative. And the thing you don't want to do to this is you don't want to use the quotient rule. Why is that? It looks like it's a quotient rule, right? There's a fraction there, for example, but only the numerator varies. It's only part that has x. The denominator is constant. If the denominator is constant, you can re-express the function in this way. The function we're working with is no different than 1/2 times e to the x plus e to the power negative x. That is a constant multiplying, so we get to use the constant multiple rule in place of the quotient rule. If you can ever make that happen, that's always a good idea. And it happens on this one as well. Just as a reminder, if you see 1 over x as a function, quotient rule is a bad call on this one. Call it x power negative 1, and the y prime would be negative x power negative 2. Same idea here. Try to get out of a more complicated rule if you can, and you're always working as best as possible. Maybe another way to say it is you don't want to use your biggest sledgehammer on a problem that's actually kind of small, really. I'll take this 1/2. We'll differentiate with respect to x, e to the x plus e power negative x. So now we're going to start differentiating on this step here. It becomes 1/2 times derivative of e to the x. That's terrific. It's just itself, no change. This one does change. Anyone see what the derivative must be for e power negative x? Good call. This one is tricky because a chain rule comes into play. When you write down e power negative x, that's the derivative of the outer function right here. But when you throw in the negative one, that's the derivative of the inner function, negative x. Derivative of negative x is a negative 1, so it gets produced right in that location. These are always kind of tricky to me. Oftentimes when I'm differentiating these, I miss that there's a chain rule, which means I'm missing a negative 1 right there. So if you're missing a sign, it could be something like that in this problem. Well, then this turns into, we can bring this 1/2 back together, put it down into a denominator. So 2 goes down below. Copying, this is e to the x minus e negative x. Take a look at our definition for the original hyperbolic sine. Should be just like hyperbolic cosine, except there's a negative right there. That's exactly what we wanted. So this equals sine h of x, our hyperbolic sine. Well, we did it, folks. This one is not a real homework like you'd see, or a real problem like you see in the homework or an exam. It's more of a derivation of this one, but it's cool to know you can prove these from first principles just in this way. Did not work that way in section 3.3 on trigonometry. When our author was trying to come up for the derivative of sine to get a cosine, that was a fantastic amount of algebra that went into play. Our author used geometric arguments, lots of triangles and such, to finally make the limit work. But here, we know the definition of hyperbolic cosine, so we just differentiated and we're done. So hyperbolics are nice, they're easy to work with. They're just strange because we don't really focus on them a lot. Well, let's try another one. Let's make this our part A to say we're doing this officially. Instructions are just to differentiate, find the derivative. And our first one, definitely before that application, let's hide it. We'll go like this. Let's let it be f of x equals cosecant h squared of x. So that's our first official one to start us out today. And just like dealing with that negative x right here, this one becomes a chain rule altogether. There's a power 2 function, and then there's a hyperbolic function. To see the chain rule a little bit better, you could start your answer by going like this. f of x equals cosecant h of x to power 2. In this configuration, it's more clear that that's the inner function. We'll handle second. And power 2 is the squaring function. The outer function will handle first. Now let's go and actually take the derivative of this thing. The derivative of f at x, first 2 comes down, becomes a coefficient. The new power here is 1, so I just won't write it in. I don't want it to look like a prime symbol on accident. And then through the chain rule, we multiply by the derivative of something. That something is the inner function, hyperbolic cosecant. So cosecant h goes here with its input x, and cosecant h goes here also with its input x. So that's our first run on this with the chain rule. Last thing to do is just crank out that derivative here. Now, if you work by analogy, this is not a bad strategy. You could say derivative with respect to x, cosecant x, is negative cosecant x, cotangent x. You just have to be mindful of the negative sides. This one is the right value to expect. The negative is in the right position, but the thing to watch out for is definitely that one right there is unusual. That negative side doesn't feel like it belongs, but it truly, truly does. And it's missing right there. So if you're well aware of row 2 and the trickiness that happens, everything else is similar by analogy. We're just putting in an h to say it's a hyperbolic function. That's the major difference. So for this one here, the problem will end by saying f prime at x is equal to 2 cosecant h of x times, now this part will be the derivative. Let me highlight it this way just to express it. This will come in as a negative cosecant h of x times cotangent h of x. Last thing we have to do is simplify, but it's nothing major. We're just going to combine the like bases, the hyperbolic cosecant. Also, we might as well take all the coefficients, put them out front to produce negative 2. Then cosecant h squared of x, cotangent h of x, is the last bit right there. That finally gives us our full derivative. Well, we did it, folks. Any questions on the result here? Okay, when we're doing these kinds of problems, I want to highlight the things that are really, really easy to miss. It's sometimes easy to miss the x's. These have to be there, but that's not the major danger here. Nonetheless, let's say it anyways. X must be here and here. But the bigger danger in these problems is we have to get used to writing down that h right there. That's easy to miss. And if we don't put it in, we're talking about a totally different function. Its plot is different, its outputs are different. So even though it seems small, that h is actually worth some points right there. And same with this one right here. So I'll say here, h must be included. So that h for the hyperbolic is easy to miss. So always watch out for that. Aside from that, we're doing some pretty normal derivatives. In a certain sense, I still feel like this section, it's kind of like a break after the second exam, doing related rates and all that difficult stuff. It's kind of a rundown of trigonometry as well, with a small change in some of those derivatives. So think of this as kind of a relaxing homework set. We're going to just practice and take some more derivatives. Any questions first before we try another? Okay, this one was chain rule, so let's change this up a little bit. We got to do a good quotient rule problem. Let's let this one be y equals, and how about 5 sine hx divided by cosine x. There's something about this problem which is absolutely nasty. Anyone see what's nasty about this question? It's not really the quotient rule. Exactly. These functions can now get mixed. It's up to us to spot the difference. After section 311, there's no requirement that hyperbolics have to be alone and ordinary trigs have to be alone. So good height on that one. On the numerator, we have a hyperbolic function. We'll treat it in the normal way, but not in the denominator. It's also a quotient rule, so we'll be careful to write this out as we get going on this one. Let's start with a ordinary dy dx, or y prime if you prefer. Think of this as the top function that will handle, and this as the bottom function that will stay in the bottom squared. First thing we have to do is differentiate that hyperbolic sign. Well, sine turns into a hyperbolic cosine. The 5 here is multiplying, so constant multiple rule says turns into 5 cosh x. So I differentiated there. I'll put this in black since I'm just going to copy cosine x. Minus is in the middle. We're just building out the numerator so far. I'll put in the numerator of 5 sine hx. Multiply by the derivative of cosine. And anyone recall what that derivative should come out as? Absolutely, we get a negative sign on that one. And that fills out our numerator. Then down below, we're just squaring cosine, so it's a cosine squared of x. Again, it's really critical to spot the difference on this one. If that was a cosh x, then when we went to differentiate it, hyperbolic cosine of x turns into hyperbolic sine of x. That looks extremely weird because there is no negative sign on this one. This is another one of those hyperbolic functions that don't match the pattern we're expecting. But since we know it's an ordinary cosine, we knew to throw the negative sign right in that location. From here on out, let's take a look at the function. I don't see a single thing that can really simplify on this. Probably the only thing I would do to it is clean up some of these negative signs. It becomes 5 cosh x. You could factor out 5, but it's okay to just leave it distributed. Cosine x goes here. This will be plus 5 sine h of x times sine x. These don't combine. We have to leave them separated out. And it's all divided by cosine squared at x. So kind of a strange problem. Really, I think the bigger takeaway on this problem is spotting the difference when you have a hyperbolic versus when you don't. Can make a world of difference when you go to write out your derivatives. Also, when we go to write our answer, be sure to put an h here and here coming from the original hyperbolic function itself. Those are easy to miss for sure. Well, let's try out another one. Any questions or comments at all with this one here? Okay, well, that's 2 derivatives down. I think we have some more interesting ones to give it a try. So let's try this one out next. Let's call this part C. And the one for part C, let's see, we've done quotient rule, chain rule. We ought to do a product rule next. This one goes f of x equals x tan h of x minus cosh h x. So it's not just a product rule. We also have a difference rule because of that negative there. But right by the red dot, because those are 2 functions of a variable x multiplying, we must use a product rule in that location. So let's give this a try and see how it goes. First thing I'm going to do is, when we go to write out the derivative, f prime at x, let me color code these 2. That's where the product rule is going to happen, just in that spot. With the color coding, I'll only show the color coding when a derivative happens and copy in black when we're just copying the expression. So first thing I would differentiate is x. If you're differentiating hyperbolic tangent first, good call. That's really more of a stylistic choice, would be just as fine. Going this route, derivative of x would turn into 1. And then we have to copy down hyperbolic tangent. Then go plus, copy our x in. Now we take the derivative of hyperbolic tangent right here, If it was ordinary tangent, it would be secant squared. And for this one, well, it's hyperbolic secant squared. This one is exactly the same, no trickery on the negative sign. So tangent h squared at x. So that was the product rule going from here to here. Next, we have another constant multiple rule. The -1 just stays a -1. Derivative of hyperbolic cosine turns into hyperbolic sine. Then the problem is done right at that stage. These go really rather kind of quickly, but it's because we've practiced product rule, quotient rule, chain rule, and all that good stuff for quite a few sections. We're on the 11th section of chapter 3 already. Yeah, go ahead.
Can we put the final one, or do you still differentiate that in the third? What does that mean?
Oh, it would be. That was a mistake on my part. I'm really not sure why I put that there. That should have been just as you said. Let me put this in red. That one was definitely a mistake. It is secant h squared of x, just like that. Thanks for spotting that one there. Other questions or comments? Usually when I find a mistake, I try to squint at it a little bit harder because if there's one mistake, there's a potential for another one, but I think we've got it in at that format. Really not too much to do. It's kind of in a weird format with the 1 times. So if I was to take another step on it, I would just recopy tangent h of x plus x secant h squared of x minus sine h of x. But if you didn't even put that times 1 there because you're just fluent with the product rule, you just wrote that out, then good on you. That's kind of the point that we want to try to get to after practicing all these formulas. Well, let's try another, and then maybe we'll take a peek at that application right after. So here's our part D next. Let's see how this one goes. We've done just about everything, but you know what? This one's a good one. Maybe one more part after this one. This one's pretty short. This one's going to say g of x equals secant h squared of e to the power 4. Has anyone spotted what the derivative should be of this one? Good call. I have no idea what this number is equal to, but it's a constant. No x is involved whatsoever at all in this expression. So its derivative must be 0. If we wanted to calculate it, it's not too bad. Go to any calculator that you're happy with. I think Desmos is pretty good unless your calculator does have hyperbolic in there. If it doesn't, you would have to use 2 divided by e to the x plus e negative x as your formula in your calculator. But here you could go hyperbolic secant. I think we're going to test this out. Secant h, e, power 4. Yeah, it knows about the hyperbolics. Power 2, I want to put it on the outside just so I have a good value. And it turns into basically 0. This is 1.5 with an order of magnitude of -47. I think that's smaller than the tiniest things that people deal with in physics. But it's constant either way we look at it. So the derivative must be 0. Well, that one is kind of strange. Always watch out for that concept of, is it really constant or does it vary? It's the missing x here, which is giving us a 0 derivative on this one. Let's do a real problem that's not a trick question like that. Here's our part E. It goes f of x equals sine h of ax plus b times secant h of alpha x plus beta. Really weird problem, and it's kind of similar in spirit on what's happening in part D. The derivative isn't 0, but in part D, the way we got through it is we had to know what was constant and what varied. In this problem, the actual variable is x, indicated because we said f of x is equal to the function. That means a, b, alpha, and beta, they're all going to be constants in this problem. Let's say that right here. A, b, alpha, beta, are all constant. Because they're constant, if you were to take the derivative of, say, this right here, y equals ax plus b, then the derivative of y with respect to x, anyone see what the value should be for just a simple derivative right here? Absolutely. The variable is x, it's to a power 1, it will vanish in the derivative. We get just a then, a b is constant and it's added on, not multiplying. It must go to a 0 in this problem. So that's not the full derivative, that's just a small part, the inner portion right here. But this problem looks like it's going to be maybe our last one before we try the application, because it's a little bit nastier. There's a product rule to start off for sure, and the inputs to the function are not just a simple x, it's a function of x, and so now we have the chain rule all at the same time. First, let's think of it as product rule. That'll be the first factor, this will be the second factor. Then we'll drop down to the derivative right away and say f prime at x equals, first I'll differentiate the hyperbolic sign right here. Well, first, even before that, let's recall it's a chain rule. This will be derivative as the first one as the outer function, and this one will be the inner function we handle next. So hyperbolic sign turns into cosh, multiply by the derivative of something in that way, throw the inner function in both slots, ax plus b here and here, and that takes care of the first portion. We just need to copy that second factor hyperbolic secant. So this problem is looking pretty long. It's already taking up about 70% of my horizontal space just to write down that first step. So I'll use this strategy. If your problems ever get really long, you can drop it on another line in this kind of way. So it's going to be all of this plus. Next, I'm going to copy down hyperbolic sign. This is the one to copy this time. Ax plus b going in here. Now differentiate hyperbolic secant. Question for the class. Will we get a negative sign or a positive sign in that derivative? Good call. This is the odd one out. This one gives us a negative. So brackets here at a negative. Like before, it still is a chain rule. Here's the outer function, 1. Here's the inner function, 2. But first, I want to write down the derivative of hyperbolic secant. I mean, we have it sort of. There's the negative sign. The rest of it is going to be secant h of something times tangent h of something else, then multiply by the derivative of whatever that something else happens to be. So 3 positions this time. That's because the derivative of hyperbolic secant involves 2 inputs altogether. Take alpha x plus beta, and it goes into all 3 slots. Oh, I did forget one thing. This is a bad habit of mine. If I put something down like this because I'm thinking chain rule, I should remind myself to differentiate. Missing that is an easy way to make a simple mistake and just totally forget to differentiate at all. So now take this, alpha x plus beta. It goes here, here, and here. So let me now, I think we can get this on one line if we really plan ahead and try. We're ready to write down our final answer. We'll need to crank out this derivative and this derivative here. Any questions first, folks, to this stage? Okay, so like our warm-up problem right here, identifying the constants gave us the derivative through chain rule. So derivative of ax plus b is just an a. I'll put that in blue because that's a derivative we calculated. And anything we copy, I'll just put in black. So there's the a. Then it's cosh ax plus b. Then this has been handled. The a went out in front. Copy secant h. Alpha x plus beta. Then more copying on this, but before I copy in that value, let's do this derivative as well, matching the pattern. So derivative of alpha x plus beta just turns into an alpha, so we'll go plus Oh, well, it's not quite plus. There's a negative sign right here where you have to work with. I always kind of forget those. I'm going to put in a minus beta. Or excuse me, a minus alpha. So I did two things here. I got alpha from that derivative. I took the negative sign with it and put it out in front of hyperbolic sine. So now let's copy this portion. Sine h, ax plus b goes in. We took care of the negative sign, so we just need to copy secant h, alpha x plus beta. And this is the last one. We took care of the derivative. So this is tangent h, alpha x plus beta. Hey, it fit. That's always kind of a good time if you can make it fit on one line like that. And that's about as nasty as a derivative as we could see in this section. Any questions at all, folks, on the end stage of this one? Okay, well, these are the major kind of things that we'll be doing in this section. And after this section is over, we'll finally be in chapter 4. So congratulations, folks. It feels like midterms is about over and we're moving ahead in the course. But I felt like for the last portion to do today, we ought to try an application. Does that sound all right, folks? One last application before the weekend? Okay, let's give this a try. The reason for an application on this one is, well, we already are very familiar with loads of applications to trigonometry. Anything that's cyclic or periodic, like temperatures, waves, things like that, you can model with a periodic function. Hyperbolic functions, they do have applications too, and this is a pretty decent one. Here it says, if we have a water wave with length L, so that's the length of the wave, if it moves with a velocity v, we have a v right here, that's a dependent variable, in a body of water with depth d, d is right here for depth, then the velocity of that wave is modeled by this format right here. The square root of g, that's the acceleration due to gravity, so lots of physics went into this. L, the length of the wave. 2 pi makes it come back on this one, and I'm not really sure why. I'm not familiar with the derivation. And here's our hyperbolic right there. Hyperbolic tangent of 2 pi times the depth of the water divided by the length of the wave, where g is acceleration due to gravity. And we want to explain why that might be an appropriate approximation in deep water. So that is a decent application to dealing with hyperbolic functions. There's many others, but they're usually a little bit more esoteric compared to trigonometry. When it says, explain why this approximation is appropriate in deep water, it does give us a hint on what we're going to do on this. Talking about water is talking about the depth right here. And the depth only appears in one location right here. I don't think I have a good way of even highlighting that. It's right here by that pi. So if we're talking about in deep water, we're making the depth larger. Does that make sense to folks? And if we're making the depth larger, they didn't say by how much. It might mean we're really doing this. We're taking the limit as the depth goes to infinity and just seeing what happens to this function. That's weird. We don't have any concept of infinite depth when it comes to water and waves, but this is a way to see why maybe this is still a decent approximation. So we want to take the limit of this function here, GL divided by 2 pi. This is the special part, hyperbolic tangent, h of 2 pi d divided by L. So that's a limit that we would like to take. Dealing with this limit is tricky. It's very much like, say, dealing with a limit with, say, e to the x, e negative x, or anything along those lines. Those kinds of limits really require graphs. And we saw those kinds of limits when we were in section 2.6, quite a ways away. The good news for us, though, is we do have a graph for hyperbolic tangent. We're going to go cite what the graph looks like and use it to evaluate the limit. So let me scroll up for just a moment. Not that far. We want to go to, let's see, it's graph and then function. So hyperbolic tangent is Where to go? This one right here. Almost looks like a tangent inverse, but it definitely isn't. Let's go back down to our application and put this in as our hint on how to even get across that limit. So looking at this page right here, or this graph right here, we can really come up with two limits. We could say the limit as x goes to infinity of tangent h of x. If we're going off to infinity, then we're following the curve in this direction. It's going over towards a horizontal asymptote, but a horizontal asymptote tells us that's the definition of the limit at infinity. You're settling down on a value, much like a horizontal asymptote. So we get a limit of 1 on that one for that direction. And just for completeness, if we went to this direction, it would be limit as x tends towards negative infinity, tangent hyperbolic of x. And this one's tending towards -1. It'll never hit it, but you can get as close to -1 as you like by taking your input x to be sufficiently large negative. So back to this function up above, we're going towards the positive direction. We're taking the limit of a hyperbolic tangent. There's a lot of constants inside, but still, with whatever those constants are doing, the variable d is much like the variable x. The whole thing is just approaching 1 altogether. So this turns into, just immediately, the limit as, oh, I don't want to go that step. I want to kind of go like this, square root of GL 2 pi. Now we're taking the limit as the depth goes to infinity of hyperbolic tangent h of 2 pi d divided by L. Much like x right here is a quantity that's just getting larger and larger, so is 2 pi divided by L times d. This is just going to get larger and larger as x tends towards infinity. So its entire value becomes 1, just like this limit right here. Does that make sense to folks on this evaluation? Okay, so finally, after we take that approximation, we get the square root of GL over 2 pi times 1, so we can even leave that 1 off. And this is our explanation. So this is the velocity for typical depths, but if we're dealing with very deep water, that in the limit it becomes this value, and that's why we have an explanation for this right here. We can say, just to tie it off, this shows that v approximately equal to the square root of GL divided by 2 pi. That's harder to type than I thought it would be. 2 pi is appropriate. Well, that's a standard kind of application towards the hyperbolics. There's many more, like if you're hanging a wire between 2 telephone poles, the actual shape of the wire is called a catenary. That's modeled by hyperbolic functions as well. So there's loads of these kinds of things. I felt like we ought to do at least one before we finish off this section. Well, any last questions or comments, folks, on the end of these notes here? Okay, we ended a little bit earlier today. Sorry about that. But if you do have questions, I'll be available and happy to help out. Otherwise, have a great weekend, folks. If you sleep in this entire weekend, then it's probably warranted. We're past midterms finally. Congratulations. Oh, that means we're 50% done with this class too. It's awesome.